Hi everyone, welcome to the class. So topic for today, the class is labeled advanced topics, but really what we'll be doing is we'll be looking at expressive power of graph neural networks and see whether that expressive power can be improved or increased. The way we think of, right, kind of a recap now back to graph neural networks is that basically given the input graph, we were thinking about these computation graphs, and we propagate information through several layers. And when we think of this, is that we have the input graph, we have the graph neural networks, we obtain the node embeddings, and then we attach some prediction head to it to make predictions. We have the evaluation metric, we have the loss function, and so on, right? And today's lecture, the key question we'll be asking is, can we make the representation power of GNN more expressive? So really, this is what we are going to talk about today. So first, I want to highlight some limitations of graph neural networks, and then I'll show you kind of two principles, two solutions to address them. So here's kind of what a perfect graph neural network would do, right? What should a perfect graph neural network do? Right, it should provide me basically a k-layer perfect graph neural network would embed a node based on the structure of the k-hop neighborhood around that node, right? So a perfect GNN would build an injective function between the neighborhood structure and the embedding, right? So every node should be mapped to a unique, or every network neighborhood should be mapped to a unique position in the embedding space. And just kind of to clarify, for today's lecture, I'm really going to focus on the graph structure, and I'm going to kind of ignore a bit node attributes, right? I will assume that, node features are kind of the least informative and things like that, and I will really focus on capturing the graph structure, right? So what I'd like, if this is a neighborhood of a node two-hop neighborhood, each unique neighborhood should map to a unique position in the embedding space. That would be the perfect GNN. That would be the most expressive GNN I could have, right? So here's an example, right? For a perfect GNN, two nodes that have the same networking neighborhood structure should get the same embedding. So for example, if I have two graphs and I say what should be the embedding of V1 and what should be the embedding of V2, then these two nodes appear exactly in the same graph, so they will have the same embedding, right? Again, let's assume, let's kind of don't worry too much about node features, right? But what I want is these two nodes appear in the same network structures, so I will give them the same embedding, okay? And right, if two nodes have different neighborhood structures, then they should get different embeddings, right? Node V1 appears in a different network than V3, so the embeddings should differ, right? We kind of all agree, right? If we focus only on the network structure. I want the embeddings here to be different because I want to distinguish the difference, and here the embeddings should be the same because the network structure is the same. So all sounds good. However, this may not always be the case, especially this is the second one is what we care about, right? Even though if two nodes have the same neighborhood structure, sometimes maybe we want to assign different embeddings to them, and I'll give you an example of that. And because nodes that appear in different, for example, the reason for this is for nodes that appear in different positions of the graph, and I'll explain what I mean by that. And we are going to call this position-aware tasks, and I'll talk about a class of graph neural networks called position-aware graph neural networks. What's an example of a position-aware task? Imagine you live in Manhattan. Manhattan looks like this to you. A graph neural network won't know whether you are in this corner or in that corner because the network neighborhood around both of these looks the same. Right? Still, you'd like to know that you are at the bottom left of, southwest of Manhattan or in the northeast of Manhattan, right? And by Manhattan, I mean, it's a grid, again, and assume no node features, right? So that's what I mean by position aware, right? And a graph neural network will give you the same embedding for these two nodes, even though they are on the opposite sides of the network. And then also the second observation is about different network structures, which we would like to map into different embeddings, right? In lecture 9, right, when we talked about how powerful are graph neural networks, we discussed that the expressive power of GNNs is upper bounded by the expressive power of the Weisfeiler-Lehmann graph isomorphism test. And one simple example where this breaks is, for example, GNN cannot count the cycle length, right? If you are a node on a cycle of length 3, or you are a node on a cycle of length 4, your computation graphs will be the same, right? You are a node, you have two neighbors, each of the neighbors has two neighbors, and you can go make this as deep as possible, but the computation graphs between V1 and V2 will be the same, so the GNN won't be able to distinguish these two network structures. Again, I'm not assuming any node features or attributes that would help me with this. So the plan for today's lecture is to look into these two kind of observations or issues. One is the observation number 1, where we want nodes, even though they have the same network structure around them, we want them to be embedded in different points. This is called position-aware graph neural networks. And then the second one, which says that the graph neural network cannot count the size of the cycle, I'll talk about a very simple idea called identity-aware graph neural networks that actually allows you to increase the expressive power of the GNN. So that's the plan for the lecture. And if we have time, I'll briefly mention a bonus topic at the end. Okay, that's the plan. So here is our approach and how we are kind of going to think for the rest of the lecture. Right? The idea is that given two different inputs, we think of them as being labeled differently. And we'll say that, kind of a failed model will always assign the same embedding to these different inputs. And a successful model will assign different embeddings to these different inputs, right? And the key kind of reasoning that we are going to do is to realize that the embedding created by the GNN is determined by the computation graph. Right, so here I have two nodes V1 and V2, and imagine that V1 is labeled with label A, and V2 is labeled by label B. The goal now is that I want to do, let's say, node classification, and in order for me to classify this one in one class and classify the other one in the other class, this means that the embeddings of these two nodes have to be different, right? So, but will this actually happen? And as I was showing you earlier, this may actually not happen, right? If I'll show you, I ignore these zeros and ones for now, but imagine I have two different cycles, and all the nodes have no features, or all the features are the same, so their computation graphs will be exactly the same. So the embedding of V2 is going to be the same as the embedding of V1. So you won't be able to distinguish between them, so you won't be able to classify one into class A and the other one in class B. You'll either classify both. Basically, they will be assigned the same class. So what would be a naive solution to this? One naive solution, kind of, I would say, the warning is don't actually try this because it's naive, but, to give you a flavor, would be that we can assign each node a different ID. Then we can always differentiate between different nodes. So I could say, this is my node 1, this is my node 2, and this is my node, let's say 4, right? I'm just using this one hot indicator to label, to account for the nodes, right? And now everything becomes distinguishable because this one has neighbors with the one at the last spot and the one with the second spot, and this one has neighbors at the second spot and the second spot. So we are able to distinguish this. Okay, so this would be one possible way to say, okay, now I can actually distinguish these two nodes. And as I'm looking at this, here's actually a bug, right? It should be no, it's not a bug. It's all good. Okay, I'm just maybe, yeah, didn't see well. Okay, great. So that's one way how you could try to distinguish these things. The issue is that now you need a one hot encoding for every node, so the dimensionality of every node will be proportional to the size of the graph, which is unfeasible, and it's not inductive, right? I cannot generalize this to new graphs. I don't know how to label or how to assign these IDs to new graphs. So this is why this is a bad idea. But let me tell you now how one possible solution to this that's called position-aware graph neural networks, okay? That are going to solve for this. And here is how we think of this, right? Imagine that kind of generally speaking, there are two types of tasks, like again, just, you know, approximately, two extreme types of tasks in, let's say, node classification in the graph. One is what you could call, or what we call structure-aware tasks, and this would be a structure-aware labeling of the node, right? Like, no, these two nodes have the same network structure around them, so they get the same class. These two nodes have the same network structure around them, so they get the same class. So this would be like structure-aware labeling, just as an example, right? And here is a position-aware task, right? Nodes here on the left are labeled with A, and nodes on the right are labeled with B, right? And the point is the following, right? For structure-aware tasks, the computation graph of nodes labeled with A is going to be different than the computation graph of nodes labeled with B, right? Because here he has 3 neighbors, this node has 2 neighbors. So that's already a difference. So the GNN will be able to distinguish between these two, and GNNs will work beautifully, and you'll be able to learn this classification. Okay? All good, right? How about the position-aware labeling of the graph, right? Here's this, what I would call position-aware labeling of the graph. So let's take, this node labeled with A, and let's take that other node labeled with B. Let's look at their computation graphs. Actually, computation graphs are identical, and you can go as deep in these computation graphs as you want. They will still be identical, right? Because the two nodes, their positions are isomorphic to each other, right? So the V1 and V2 will always have the same computational graph due to the structure symmetry. So the question becomes, what could I do so that my GNN would be more expressive and would be able to capture this difference between nodes A and B and learn that, one set of nodes should be labeled one way and the other set of nodes should be labeled the other way, okay? So that's the question we are trying to address to make GNNs work with this kind of graph labeling task. Okay, so the key concept that I'm going to introduce, right, is the notion of an anchor. Okay, so we are going to have this notion of an anchor, and then we are going to generalize it to the notion of the anchor set. Okay? The idea of the anchor is that anchor gives you like a reference point, right? The problem with graphs is that there is no reference point, so you don't know in what part of the graph you are. So anchors will provide us reference points, right? So the idea is that I'm going to, in this case, let's say, randomly pick a node, let's call it S1, and I'll define that that's an anchor node. So now I will be able to represent positions, V1, V2, as some kind of how their positions relate with respect to the location of the anchor, right? So in some sense, what we are going to do is we are going to develop some kind of positional encoding in the graph so that nodes understand where in the graph they reside. That's another way to say what we are doing, right? So anchor serves as a reference point and can be used to basically locate or define the position of the node in the graph. So if this is my anchor, then for example, and let's say I quantify the distance using the shortest path, then V1 is 1 step away from the anchor, V2 is 2 steps away from the anchor, right? So now if I would use this as positional encoding as a property of the node, then the neural network would be able to distinguish these two nodes because they are at different distances from the anchor, okay? And to make the entire thing more robust is we can pick even more anchors. We can have one anchor, here's the second one, and the observation is that more anchors can better characterize nodes' position in different regions of the graph. So we want to have many anchors, and now we have kind of multi-dimensional positional encoding of the node in the graph. What turns out to be also very, very useful, and I'll show you some theory behind it, is that we can generalize this notion of an anchor to a notion of an anchor set, where an anchor set is a set of nodes, and now a distance of the node to the anchor set is the minimum distance of the node to any member of the anchor set. Okay, so it's like what's my distance to the closest anchor? It's like what's my distance to the closest petrol station? And there's a lot of petrol stations around. Okay, so why is this helpful? Because large anchor sets sometimes may provide more precise position estimation, and we can save on the total number of anchors. Right, so for example here, I denoted it here, that the disk S3, right, so this would be node S1 and V3 is a size 2 anchor set. And now the encoding would be, for example, V3 is part of the anchor set, so it has distance 0 to it, while V1 has distance 1 to the anchor set, right? And the point is that if I would only have anchors S1 and S2, they cannot differentiate, in my case, nodes V1 and V2. But this kind of bigger anchor sets, where I choose the distance to the closest one, allow me to better differentiate. Why do you do this way? There's actually a very good theoretical mathematical motivation to do that, right? The way you can think of this is the following. I'll kind of paraphrase a bit of math here to give you the intuition. What we want to do is we want to embed metric space of vertices and a distance function into the Euclidean space, into k-dimension Euclidean space, such that the original distance metric is preserved, right? So it means for every node pair UV, the Euclidean embedding distance between their embeddings we want it to be close to their original distance in the network, okay? And then there is a beautiful theorem that kind of keeps popping up over and over again. It's called Bourgain's theorem. And here is what Bourgain says, kind of informally, right? Imagine that I am considering the following embedding function. So the embedding of a node is simply the minimum distance of the node to the first anchor set, to the second anchor set, and I sample log n, and I sample anchor sets where the size of where the first index is the number of anchor sets of a given size, and the second index is the size of the anchor set, right? Here C is a constant. Sij is chosen to include each node independently with probability 1 over 2 to the I. So it basically means that as I'm sampling smaller anchor sets, basically as I go more to the right, my I is going to increase, so the anchor sets are going to get exponentially smaller, but there is going to be exponentially more of them. Okay? And here in my case, the distance between the node and the given anchor set is the minimum distance between the node V and any member of the anchor set. And what's the point of all this? The point is, if you construct your anchor sets the following way, then the embedding distance produced by this embedding F is probably close to the original distance metric. That's kind of the key. This is why we care about this. What is happening here is basically that we are generating multiple anchor sets of bigger and bigger sizes, but having fewer and fewer of them. Right, so we are going to have a lot of anchor sets of size 1, fewer anchor sets of size 2, even fewer anchor sets of size 3, and so on. But we are going kind of to have this many of them with increasing sizes, but with decreasing numbers of them. So that and if that is happening, then the following fact is true. Yes.
So like, how is this embedding different from node to vec? So in node to vec, will be also like generate some embeddings for the nodes.
Good question. So the question is, how is this embedding different from node to vec? Node to vec, the intuition there was to predict these neighborhoods. And what I showed you in terms of theoretical properties, node to vec kind of boils down to a particular matrix factorization approach of a particularly transformed your graph adjacency matrix, right? I think I showed you some ugly fat equation, right? Here, this is different. This was actually, the Bourgain theorem was developed for vector spaces, right? And here I'm rephrasing it in terms of the graph. But the idea is that basically if you have a high dimensional space, then you can basically define a set of anchors in this high dimensional space, determine your position according to those anchors, and the distances are going to be preserved. So this is much more kind of geometric intuition. Okay? Yes?
In practice, does it matter what we pick for a distance metric?
Good question. So the question is, what do we pick for D? What people like to pick in graphs is the shortest path distance. You could also do some kind of more random walk distance or something like that that you would try. I mean, this will depend on the application, but I think the point being, good question. I think the point is that this distance has to be that distance, right? So these two distances have to be kind of compatible. Okay? Yes?
So if I want to embed multiple different graphs into a vector space, does it matter each of the graph have the same consistent anchor selections, or I can have a different type of anchor select for each of the different graphs?
Great question. So what you were asking me about, if I have multiple graphs, multiple anchor sets, what do I do? Let me address that later, because what you are really asking me is, this kind of inductive versus transductive. Because as soon as you define an anchor set, you have forced yourself to pick a set of nodes, and that's problematic. I'm going to address that. Okay? The motivation for development of the position aware GNN is basically follows this Bourgain's theorem, right? Where basically the idea is that we are going to sample some logarithmic number squared of anchor sets, and then embed each node based on the distances to these anchor sets. And what then becomes harder, and this is exactly the question you were asking me, is how do you maintain inductive capability? How can you generalize from one graph to another graph, because nodes are different, anchor sets will be different. And the way this is solved in the paper is that during training, new anchor sets are resampled every time. So you kind of make these anchor sets move around, and the position aware GNN is learned to operate over new anchor sets. And at the test time, when given a new graph, you can simply kind of sample anchor sets at random. To summarize, what is important is that when you represent the positional information, we represent node by its positions to randomly selected anchor sets, and each dimension of the position is tied now to a given anchor set. Now, how do you use positional information? I would say the following. If you are inside one graph and you are learning like in a more kind of semi-supervised setting way, then a simple way is to use this positional encoding as a simple augmented node feature to add this additional information to the GNN to be able to learn. And that works really well in the kind of semi-supervised learning where you are given one graph and the anchor sets can be fixed. Now, if you want to, the issue with this is that each dimension of the position is tied to a particular anchor set. So the dimension of the positional encoding kind of cannot be changed or randomly permuted without changing its meaning. So the position-aware graph neural networks paper actually develops a special neural network that can maintain this permutational invariant property of positional encodings. And permuting the input feature dimension will only result in the permutation of the output dimension. And this means that the value of each dimension won't change. And more details are in the position-aware graph neural networks paper. But the idea is the following, right? If I look at my distance towards all size 1 anchor sets, then if I have sampled enough size 1 anchor sets, then of course I sampled them in different order, but kind of my distribution of distances to them will kind of be unchanged if I'm in a given part of the graph, right? Kind of in the limit, right? So that's that. When I say this permutation invariant, I want my positional encoding to depend on the anchor set size, but not the exact locations or positions or the order in which I sampled the anchor sets. That's, further details in this paper. Yes?
Can you go back 2 slides?
1, 2.
Oh, sorry, to the slide that has Bourgain's theorem embedding function.
Yes.
Just a clarification question. If we use the embedding function that is described there, the application of this is that it's only used in the first layer. We initialize our node features with that vector, right?
Yes. So again, let's make a difference between what the Bourgain is saying and then what we are doing. What Bourgain is saying, if you are embedding your nodes the following way, and if you are embedding them in a space that has the logarithmic size with the number of nodes, which is great, right? Exponentially smaller dimension than the number of nodes, then your distances will be preserved. We don't care, like in some sense in the position of RGNN, we don't care about preserving distances. We care about correct classification, right? So we have a bit different goal. And this is not the embedding function we are using. We learn a graph neural network to learn the embedding because we want to do downstream prediction. But our choice of anchor sets and why we like them is motivated by the Bourgain theorem, right? So it's not that Bourgain is a motivation. It's an abstract motivation, not a. We don't follow it strictly. So that's a good point. Sorry if that was confusing. Yes?
If you go back to where we are forward in the slides, where you say that this is sort of like forward again. Still more forward. Yeah. Okay. So is this saying essentially that the distances to the anchor nodes for each individual vertex is sort of like follows the same distribution each time you relabel the anchor nodes, so that that distribution is sort of invariant?
That's basically the idea, exactly, right? If I sample, I don't know, if I'm in a graph and I sample 100 different nodes and I look my distribution of distances to those, that distribution will be quite stable regardless of which specific 100 again is I pull that number out of the hat. Of course, it will depend, but kind of that's the idea that kind of stabilizes. Based on the structure of the graph, right? Yeah.
I haven't been able to get my head around why you might want sets of different sizes. Why don't you just always want an anchor set of size 1?
That's a good question. So the question is, why is it better to have anchor sets of bigger sizes? Why not always sets of size 1? The point is the following, right? Is like the anchor set of a bigger size will require you one dimension in your positional encoding, but in some sense it will provide much more information because the variance of that will be smaller, right? Because you can think of that defines some kind of boundary and you just say how far away from the border am I? right? So it's a different type of an object that you are measuring your distance to, right? So good, yes.
In some applications, would it be better to manually engineer the constant self-settling randomly?
Good question. So the question is, would in some applications be good to maybe not sample anchor sets randomly and engineer them? I would say yes, if you have a good reason why. Again, the reason we do it randomly is because then you are I don't have to say anything about what the data you do it, right? And again, you could, I don't know, for molecules, it might be interesting to be more strategic. What are you going to choose? Okay, cool. So that finishes the discussion of my first point, which was this position-aware encoding of nodes, so that a node knows what part of the graph it belongs to, so that it can determine its embedding, its label, based on the region of the graph they belong to, and not necessarily based on the exact neighborhood structure that they have. So that was the intuition here. So let's now talk about the second issue, which we said that right in position aware, we say even though nodes have the same network structure around them, we want them to be embedded in different places. Now we are going to look at what is called identity-aware graph neural networks, and the point here is that I want nodes that appear in different structures to actually be embedded differently. So, right. So far, right, the summary is that we learned that GNNs would fail for position-aware tasks, and we developed the position-aware GNN with positional encoding that allows us to fix that problem, right? Then the question is, can GNNs perform perfectly on structure-aware tasks? And the answer is no, right? Why is the answer no? Is because GNNs kind of exhibit failure cases at structure-aware tasks at all different, at node level, edge level, and graph level, because graphs can be highly symmetric, and the WL test is going to fail. And I gave you this example where I have two nodes, V1 and V2, obviously in different graphs. But if I look at the shape, the structure of the GNN computation graph, which we established in lecture 9, that basically this is based on how the embedding of the node gets created, and if the two computation graphs are identical, are isomorphic, then the embedding of the two nodes is going to be identical. So there's no way for us to distinguish them or to assign them to different classes, right? So this is, for example, for node classification tasks. I can show you examples also for link prediction tasks, right? Imagine I have node 0, and then I have nodes V1 and V2. The question is, right, can I differentiate between, V0 linking to node V1, but not linking to node V2? Again, node V0 will have some embedding, but V1 and V2 have the same computation graphs, so they'll have the same embedding. So I will either predict that V0 links to both V1 and V2, or that it links to none of them, right? Again, my embedding won't distinguish V1 and V2, so there will be no way for us to say V0 links to one, but not the other, okay? And then how about at the graph level? At graph level, it's also becomes quite interesting, right? If I have two different input graphs, but if I look at their computation graphs, again, they'll be identical. So even at the graph embedding level, these two different graphs will be embedded into the same point, so we won't be able to classify them differently, okay? So that's kind of a set of issues with GNNs. Again, if you don't have node attributes that would allow you to distinguish this, right? Many times you'll be lucky, or I don't know, like you have good node attributes and then things start to work out, but without node attributes and just focusing on the graph structure, GNNs suffer from these problems. So here's an idea. Idea is very simple. It's basically, the idea is to have inductive node coloring, right? We can assign a color to the node we want to embed, right? If I want to do things inductively, then I always know who is the node that I care about, right? That is the root of my computation graph, right? So what if I label that node and kind of I treat that node differently, specially, right? So, let's say here the yellow orange node is the node we want to embed, and then the white nodes are the rest of the nodes, right? So then if you look at this, then the computation graph is going to look like that, right? I'm going to remember when the computation graph visits the colored node, right? So here I go to the two neighbors, and then the two neighbors, here one goes back and one goes here.